Good day, statisticians. Today, another video where now we're going all the way back to when we were looking at relationships and paired data, and we're trying to describe them using lines of best fit and stuff like that. So let's go back. Today, we're really going to be looking at nonlinear relationships, but let's go back to when we were thinking back in the day of linear relationships. So let's say we had a scatter plot that presented two variables. Let's call one of them X and one of them Y, right? And these were all observed data. We were learning back in the day to try to come up with like an equation to model this relationship. And so we had the predicted Y that was going to equal a y-intercept, which we called b0 plus b1x, right? And the b0 is our y-intercept, and the b1 was the slope of the line. And so this equation that we could come up with, and the method that we used to create this equation was called least squares regression. So we call it the least squares regression line, right? And remembered a bunch of formulas. I'm not going to write down the formulas right now that we used to derive to get the slope and the y-intercept. But remember, it had to do with the standard deviations of the x values, the standard deviations of the y values, the means of the x's, the means of the y's, and stuff like that. Remember, this was all regression to the mean. And when we did come up with a line to fit the data, and more generally, we tried to just describe the relationship. Now, when we describe the relationship between two variables, we described the distribution of a variable. We talked about the socks, the shape, the outliers, and the spread. However, when we tried to describe the relationship between two variables in paired data, we came up with the little name FUDs, which is not as cute as socks, but it works, right? Where F stood for the form of the relationship, D stood for the direction, that looks like two E's, direction, and then S stood for the strength of the relationship. And then, of course, we would follow up by talking maybe about some unusual characteristics, right? Whether there was outliers, whether we had clustering and stuff like that. And that's great. Now, in particular, some of these were kind of vague, but the form was just about whether it was linear or curved, nonlinear, like linear or curved in general. And almost everything that we saw so far in our course was linear. And then when we talked about the direction and the strength, remember we had a great little mathematical formula, something that we could calculate to help us describe the direction and the strength of linear relationships, and that was R. And recall that R, right? R was always going to be some value between 1 and -1, where 1 and -1 meant they're perfectly strong relationships. Positive 1 mean perfectly strong positive, negative mean perfectly strong negative, and of course something was close to 0, that would mean there was basically no relationship there, no linear relationship. But recall that you can't necessarily just interpret R by its lonesome, just because you get a strong R. Like say I said that there was some scatter plot that produced an R that was 0.99, right? Well, does that mean that there's a nearly perfect, strong, positive linear relationship? Not necessarily, because you might end up having something that looked like this. Remember when we saw a bunch of dots and then there was like a single dot way up here? You could have a single influential point that would take full control over R, and if it were removed, there would basically be no correlation. So remember, you can't necessarily interpret R without seeing a scatter plot. Similarly, we could have a scatter plot that was something like this. Let me draw some points. Let me make them red this time. Say I had points that kind of were like this guy, and you might look at this and be like, ooh, R equals 0.99, that seems to make sense, right? But you notice there's a little bit of curve there, and that little bit of curvature in it would mean that even though there probably is a strong positive relationship, it's not necessarily linear. So really recall when we were interpreting R back in the day, it was all based on an assumption of linearity, right? Where we could check a residual plot. We'll talk about residual plots again. We'll review them later on in another lesson, but we could look at a residual plot in particular and try to see if we saw any curvature there, and if there was curvature, then that was really how we determined linearity. Just looking at R alone wasn't enough to know if the form really was linear or not. And that's what really we're going to be looking at in this lesson today. We're going to be taking a look now at some nonlinear relationships. How can we come up with the equation for a nonlinear relation, and basically what's some of the math that justifies that, So that's what I'm going to show you a little bit in class today. So let's start with an example here. Here we have an example. Here we're looking at the monthly premium for a 10-year, $1 million term life insurance policy, right? And I'll tell you right now, I was just talking to my wife about potentially trying to get some more insurance for our family just in case something happens to us. Right now, I don't have $1 million term life insurance, but maybe I should buy in. It looks like it wouldn't cost me too much money if I look at this data here, right? as it says, the cost of this insurance varies depending on several factors, but some of those most important factors are the age of the applicant, right? And so let's try to see if we can describe this relationship between the age and the monthly premium. So personally, right now, I'm 39 years old, so I would probably pay, it looks like maybe close to $30, all things being equal per month. And if that's truly what it is, then that would be great. But notice that the value that you have to pay for your monthly premium seems to go up quite a bit every month. And if I was just looking at this carefully, is this going up in a linear way? Well, just for fun, I took all these data and I plugged them into my calculator earlier into L1 and L2, and I made a scatter plot, and this actually shows the relationship between these two variables. And if I look at that, that does not necessarily look too linear. However, I could still come up with a linear equation to try to describe these, right? In fact, if I was to look at that, what relationship do you think that is? I don't know, some kind of curve. I know. We'll take a guess in just a minute. But let's say we tried to make we tried to take a look at the information from a linear relationship. So if I did stat calc option 8 linear regression a plus bx, and I put everything in my frequency list. I don't need a frequency list here. I'm going to store the regression equation in in y1, so I can graph it on top of stuff, and I'll hit calculate and Shazam. Notice right now that based on this linear relationship, the calculator is telling me that I've got a pretty strong R for a linear relationship. I have an R of 0.9417, right? Now, just looking at that alone, that might betray the fact that this might not actually be linear at all. It definitely looks pretty strong, positive, but it doesn't necessarily. This seems to tell us that it's a pretty strong positive linear. But remember, you have to look at the scatter plot to really know what it looks like. So, and looking at that line doesn't seem to be the best description of the relationship between these variables. So, with that being in mind, how can we describe another one? Well, I'll tell you right, if you might want to guess what the relationship is here, but the relationship is not going to be linear. In fact, it's going to end up being exponential, right? The amount of increase for every increase in 1 unit in our x variable, in this case, our explanatory variable is age, is not going to correspond with the sort of a constant change in our y variable, plus or minus an error term. And so it's actually, we'll see, going to go up exponentially. So there's a couple of, I'm going to give you a quick cheat shortcut that just to get an exponential equation that is not really part of AP Stat, but the calculator can do it. So it'll at least get you a quick answer about whether it's exponential or not, at least help you see that it is in fact exponential. So if you went to Stat Calc, and now we went down here to option 0 where it says exp reg, that means exponential regression. You can just do L1 and L2. We can store the regression equation again. I'll hit alpha trace and I'll pick Y2 this time, and I'm going to hit calculate. And now notice, check this out. This guy gives us an equation, and if you look at it, it gives us an equation in the form that's Y equals A times B to the X power, right? Where and so this is obviously not a linear equation, right? And so the calculator tells me that A would be 1.16, and so this would mean and I should put a little hat there because that's a predicted Y. That my predicted Y hat, I predict that someone's monthly premium would be 1.62. Actually, I'm going to round that up to 1.1630 times, let me move this over just a little bit, that would be 1.084, always minimum of 4 decimal places here, really as many as you feel like you could put down, 470 raised to the X power. And so this would be, according to this, would be the best equation to try to describe this relationship. And notice that for this equation, the R is something much more impressive than what I actually had for the pure linear relationship, 0.99914, right? That is definitely a much more significant R. Now, remember though, be careful. This is one of the reasons why this is not an AP Stat thing. R only describes for us, correlation is fundamentally only for a linear relationship. So what does this R mean? Where does this R come from? I'm going to try to show you basically the math behind where this R comes from, because still for us, that R is supposed to be for a linear relationship. relationship. And what we're going to learn in this lesson is that behind this exponential relationship is really a linear relationship. All the methods we learned for analyzing things in a completely linear way are still going to apply here, even though this is an exponential relationship. And that sounds like I'm speaking too abstractly. We'll get down to the concrete in just a second. So now let me go ahead and graph that and see if that exponential, oh baby, look at that. Look at that exponential curve. It seems to nearly go perfectly through all the points. So me calling this an exponential relationship seems to be fairly accurate, right? It does seem like this equation right here would be a much better description. So if I was to describe this, I would say that there is a curved relationship, in fact, an exponentially curved relationship between age and monthly premium. And this exponential curve does seem to be very, very strong, and it's an increasing exponential. No, exponentials are always strictly increasing or decreasing. This is a strictly increasing on this interval as well, too, which is kind of nice. Now, but where does this equation come from? How can I justify this equation? Well, I'm going to show you that, in fact, there is a linear relationship between these two variables once you do a transformation of your data. Remember how we talked about linear transformations of data back in the past? Now we're going to do some nonlinear transformations. We're going to do transformations of data that are that will transform data in a special way. So this is a nonlinear transformation. What we're going to do is we're going to transform our data set, right? That says transform our data set by treating x the same as it always was. Or actually, let me go back here. Let me put this. So x is going to remain exactly the way it was, but we're going to take our y value and we're going to take the log of our y. Now, you could use any base you want. I like to use natural logs just because, I don't know, maybe I'm used to it from calc. And there's only two letters in natural log, ln instead of log base something. So I like natural logging. But what we're going to do is we're going to transform this data set using natural logs to try to come up with an equation. Now, why do something like that? What's going to happen is that if I take the natural log of all my y values and I plot them against x, it's actually going to create a linear relationship. So if I go over here to my calculator and I highlight L3 and I hit, say, natural log of L2, right? And what the calculator just did is it calculated the natural log of everything that I had here in L2. If I make a plot right now, if I go to stat plot, and now I plot L1 against L3, and then I hit graph. You know what? I forgot to hit zoom, right? I'm going to zoom stat. So I still have the other equations hanging out there. But look at what I just did. Me plotting L1, the ages against the natural log of the premiums, actually seemed to produce a very straight thing. Oh, you know what I just noticed what I wrote down over here? Oh my gosh, why did someone not yell at me? I wrote natural log of x. That's so dumb. It's not x natural log of x. It's obviously x natural log of y. That was foolish. I could start the video over. I'm not going to. That would, why start over? That was just a small error, right? But yeah, so x natural log of y. The cool thing here is, that this is actually a linear relationship, right? Now, why would we get a, oh my gosh, a stupid pen is giving me trouble. Why would this be a linear relationship? X natural log y. I'm going to try to show you in a couple ways. One way is first, well, let me plot here the residual plot. Remember how we learned residual plots and just show that even in the residual plot, we're not going to get necessarily any curvature. So if I hit second stat and then my residuals were all calculated for my last regression and zoom 9, take a look. Here I still see maybe a little bit of something going on here in the residual plot. Maybe that just took away a little bit of my confidence in the beauty of this perfect exponential. But it's definitely a stronger kind of thing going on than we saw before. So why should we have a linear relationship between these two variables? Let me go back to plot L1 against L3. And why does it make sense that we should have this linear relationship? Well, I want to show you something kind of cool here just a second, right? So I'll do it theoretically, and then I'll do it less theoretically. So let's say I did this. Let's say remember that the equation of our exponential that our calculator gave us was like y hat equals a times b to the x, right? And so let's think about that. Let's say I wrote down that general form of an equation. So I had y hat, right, equals a times b to the x power. Okay, now remember to undo an exponential. This is an exponential relationship here. What's the inverse function to an exponential? Well, that's a log function, right? The inverse of an exponential. If you had y equaled e to the x, the inverse of that would be the natural log of y equals x. So let's think of trying to undo the exponential here by using the inverse function. Let's just take the natural. What I'm trying to say is let's take the natural log of both sides. So let's think about what happens if you had the natural log of y hat, which would then equal, say, the natural log of a times b raised to the x power, right? Okay, so what happens when I take the natural log? Well, the left side, I'm just going to keep my plain old now natural log of y hat. I got the natural log of y hat. But on the right side, remember your laws of logs. What happens when you have a product inside of a logarithmic expression? Well, that can become a sum of two separate logs. So I can write that as the natural log of a plus, right, plus now, the natural log of b to the x, all right, okay. And so I've got that. Now, remember another law of logs would be if I can rewrite this down. I got the natural log of y hat, which would equal natural log of a. I'll just write that down again. Now remember, natural log of a, that's just some number. But let's add to that. And let's say, what's the third law, what we frequently call the third law of logs? What happens when you have natural log of something raised to a power? Well, that power can come to the outside, right? That guy can hop out front there. So I can rewrite this guy as now x, right? There's my x, and times the natural log of b. Now, I want that to be red. Let me undo that. B, right? All right, so when I look at this equation, I'd be like, okay, that's nice. What's so great about this? Well, if you think about it, this is actually a linear equation. If you have the equation y equals a plus bx, right? This is just like one version of an equation. Instead of, let me not use a's and b's because I already used a's and b's. Let me do something like, let me call it, I don't know, u v, right? Y, two other variables, right? Where these are not really variables, these are two parameters, right? Then this, in this particular linear equation, u would be the y-intercept and v would be the slope. Well, what's happening right here? Here I see, if I just look at the right side, I have the natural log of a. And do you agree that the natural log of a is just a number, right? We could call it, it's just some number, right? And I could call it anything I want, right? So this is a number. And now notice that the natural log of b is also equally just some number, right? And so this equation on the right side is actually of a linear form. You've got some number, you could call it u, plus some number, which we could call v, let's see, natural log of b could call v, times x, right? And that is a linear equation. Now notice that the linear equation is corresponding with the natural log of y hat. There is a linear relationship here, but the linear relationship doesn't exist between x and y. The linear relationship exists between x and y hat. So the relationship, if I can relationship, the pen can't react as fast as, let me turn that off. The relationship between, right, x and the natural log of y is linear, right? Not the relationship between x and y, but the x between the natural log of y. And this is true in general. Notice I prove this sort of in the general case. So when you have an exponential relationship, if you simply take the natural log of all your y values, you should produce a linear relationship, right? And so this is pretty cool. So what's the moral of the story? So if I go back here, right, and let's say I tried to describe the linear pattern between my variables. Say, remember here how in L3, I put the natural log of all my y values. If I went to my y list and I did second L3 and I hit enter, And so I'm trying to come up with the linear relationship between L1 and L3. That's the linear relationship between x and the natural log of the premiums here. Whoops, undo. Then I get an equation. It's not the original linear equation, and it's not this guy here, but let's try to see its relationship right here. So I'm going to go down here real quick. Oh my gosh, I'm like running out of space. I guess I'll do some of the work right here. Let me zoom in just a little bit here. So notice that the linear equation that this guy gave me was y equals 0.150, well, let's see, that's 0.99 plus, and then my slope was 0.08129, and then of course I have my variable x here, right? And so, and remember that's a hat, right? So, all right, so this was the linear equation produced by comparing L1 with the natural log of L2. In other words, this was the natural log of the premiums, and then the ages here was my x, right? This is really what I'm looking at here. So, all right, let's do some math to show that this equation actually yields this. And so when I wrote this down, actually what I wrote down here is kind of a lie, because remember, it was the natural log of the equation that the calculator gave me wasn't really the true y hat compared to x, but the natural log of y hat compared to x. So let's sort of undo what we did. Let's show that this equation actually is the same as this guy. All right, let's undo that. And so how would I show that? All right, so what's the inverse operation of natural logs? Exponentials. So let me undo the natural log here by raising all of this to the e power, or rather e to this power. So if I did e to this power and e to this power, you guys with me, right? Let's see here. I'm sorry, this is getting a little confusing there. E to this power, then e to the natural log of y hat would simply become y hat, right? And over here I would have e to the 0.15099 plus 0.08129 x, right, which is kind of nice. Now, remember, laws of exponents here. When a sum in an exponent can become the product of two things of the same base. So I can say that this is y hat equals e to the 0. I'm going to just change this to colors here. 0.15099, and then that would be the product of something of the same base. E to the I'll do that in the same color, 0.08129, and I'll make the x. I'm going to change the color of the x. Do you guys mind? Just a slightly different color of red, right? Okay, good. Now, undo. Now, okay, check this out. This guy is just a number, but I'm going to write it one more time further before I do some calculations with my calculator. So this will remain the same. In fact, here's a cool trick. Can't I just, well, let me just do this. I'm going to have fun. Instead of doing that whole thing, let me grab my little tool down here. I'm going to take this x, undo. I want this guy, and I'm going to do lasso it. I'm going to take this x, and do you agree that I could take this x and just sort of move it up here? That when you are, what am I doing by moving it up here? Oops, come on, you stupid pen. That I can just raise a power to a power. The product, sorry, it took me a minute to do that. Maybe it would have been easier just to write it out. But when you have the product of two exponents, you can, when you have the product of two numbers in an exponent, it's just like raising a power to a power. In other words, what I'm trying to say is if you had a to the x raised to the y, that would be the same thing as a to the xy, right? And here we basically have the same principle here, except I'm going in reverse. If I have a raised to the x times y, I can make that a to the x raised to the y power. So, okay, that's just a bunch of explanation. What am I doing now? Let me actually plug this in my calculator. So now I'm saying that the true y hat is actually equal to, what's e to this power? So if I go to my calculator and said e to the 0.15099 power, you end up getting, that e raised to this power right here is really just the number 1.1630, right? And okay, so that's nice. And then e raised to this power, right, and this is going to, of course, be raised to the x. I'll put that there. This number is really just, let's see here. Let's go to our calculator. That would be e raised to the 0.08129. And let's see, what do we got here? That's 1.0847 or so approximately. Is that right? That looks about right. And there you go. There's this would be the correct exponential equation to describe the relationship between these variables. And just check something out for a second. Holy moly. Do you notice right here, remember this equation that the calculator gave us? And you see this equation here? They are exactly the same thing. That is the fun. That's where that equation comes from. What we have is, if we're going to say there's an exponential relationship between two variables, what we really do is we first transform the data itself by using this kind of operation. For an exponential, you'll keep the x's the same. You'll take the natural log of all your y coordinates. You'll end up creating the linear equation. But remember, this linear equation isn't really y hat versus x. It's the natural log of y hat versus x. And if you really put the effort in to transform that guy back to a regular equation where you didn't have the natural log anymore, you just solved for y hat, you'd end up getting this exact same equation that the calculator would generate. Just for fun too, if we go back and we look and do the option 8 linear regression with L1 and L3 that gave us that linear, notice that this R that we have right here, the R from our calculator, 0.99914 approximately, was the exact same R that the exponential gave us, because that's what's really happening. So hidden behind all exponential relationships is a linear relationship, where it's a linear relationship between x and the natural log of our y values. So friends, I hope this was kind of helpful. I'll tell you, in terms of the AP exam, you don't have to put all this effort. I wanted to just help you really understand how this nonlinear stuff really works. In practice, all you would really need to know is how to come up with an equation and how to plug numbers in. But I wanted to get you deeper into some of this mathematical theory here. I hope this helps you. I'll assign some problems for you guys to work on tonight, and have a beautiful day. I'll catch you on the flip side.